pages to go over. I think we have enough practice with these things now to go over these last proofs quickly without much commentary. So one important example of where the f and the f-1 notation can cause trouble is how they apply to our set operations. The operation preimage, when applied to subsets of B, behaves very nicely. It preserves inclusions, unions, intersections, and differences, the four operations of set theory. And what I mean by preserves is that if you have B0 is a subset of B1, that implies that f-1 of B0 is a subset of f-1 of B1. And say the preimage of B0 union B1 equals the preimage of B0 union the preimage of B1, okay? And so on for intersection and difference. So we'll use this fact frequently, that the preimage, this all behaves very well. But for the operation, the image of a subset, when applied to subsets of A, it only preserves inclusions and unions. It does not preserve intersections and differences. But the intersection of two subsets of the domain is a subset of the image of the first intersected with the image of the second. And the same is true with set difference. This is an equality only when F is injective. Now, one more thing, the union and the intersection hold for arbitrary unions and intersections as well. I'm not going to show that, but if you remember, we've done this before and it's easy to do because B0 can just be thought of as this one set union with another set, okay? So you can just do this inductively. Okay, so let's just prove a few of these quickly and then we'll be done. So let's start with this one. So if B0 is a subset of B1, that implies that the preimage of B0 is a subset of the preimage of B1. So we assume the left, and then we're going to prove that that implies the right. So take an arbitrary element of B0. That means that it's also an element of B1. Now, just to remind us, this means all of the A such that f of A is an element of B0. So remember, it's possible that there is no A such that f of A is in B0, right? If this was your B0 and we had B0 here, then no A is going to return B0 here, right? So it's possible that this set is empty, but if so, then there's nothing to prove. If there does exist an A0 in A0 such that f of A0 equals B0, that means that A0 is an element of the preimage of B0. And since this is also in B1, then that implies that A0 is an element of the preimage of B1. And that's all we needed to show. We start with an element of B0, then it's also in B1, and then we show that if there's an element that's in the preimage of B0, then it's also in the preimage of B1. Okay. So let's do the union. So this is set equality, so we need to show inclusion in both directions. So first we'll show inclusion this way. So we start with an arbitrary element of the left side and show that it's in the right side. So take A0. Again, it's possible that this is empty, but if it's empty, then it's automatically going to be a subset of anything. The empty set is a subset of every set, okay? But then there's nothing to prove. So if A0 is an element of this, that means that f of A0 is an element of B0 union B1. That means that either f of A0 is an element of B0 or f of A0 is an element of B1. And that means that A0 is an element of the preimage of B0 or A0 is an element of the preimage of B1. That means that A0 is an element of the union. And that's what we had to prove. That's the first half. Now we have to take an element from this side and prove that it's in there. So again, this might be empty, in which case it's automatically a subset of this, but there's nothing to prove. So take an arbitrary element of this and we'll prove it's in here. So take an arbitrary element of the right side. That implies that A0 is either an element of this or an element of that. That means that f of A0 is an element of B0 or f of A0 is an element of B1. Now, if f of A0 is an element of B0, then that means that it's also an element of the union of B0 and B1. And the same thing for this. And if this is the case, then that means that A0 is an element of the preimage of B0 union B1. Okay? And the same thing is true here. If f of A0 is an element of B1, then it's also an element of B0 union B1, in which case A0 is an element of this. So in either case, A0 is an element of the preimage of B0 union B1, and that's what we wanted to prove. So we've shown inclusion both ways, so this is true. Okay, so the next two, the intersection and the difference, are going to go pretty similarly. If you want me to do them, let me know, and I will, but otherwise I'll leave it up to you as an exercise. Okay, so let's skip the subset one for A. It's easy to do too. If you want me to do it, I will. Let's prove the next one. So remember, this one is true. These two are true no matter what kind of a function f is. So to prove equality, we prove inclusion in both ways. So we'll start proving it that way. So we'll have an arbitrary element B0 of f of A0 union A1. And we have to prove that in that case, B0 is an element of this. So if B0 is an element of this, that implies that there exists an A0 inside A0 and A1 such that f of A0 equals B0, right? So that means either A0 is an element of A0 or A0 is an element of A1. That means that f of A0 is an element of f of the subset, or f of A0 is an element of the image of A1. And that means that f of A0 is an element of the union. Okay? So that's going this direction. Now, assume that A0 is assume that B0 is an element of this, prove that it's an element of this. So that means that B0 is an element of f of A0, or now B0 is an element of f of A0 means that there is an A0 element of the subset A0 such that f of A0 is an element of the image of the subset. Oh wait, no, I said that wrong. That means there exists an A0 such that f of A0 equals B0. And B0 inside the image of A1 means that there exists an A1 inside the subset A1 such that f of A1 equals B0. Now note, this is the spot where this stuff gets hard. It's really important that you're careful here. This is not necessarily the same number, even though they're both B0, because from our example, A0 could be over here, and A1 could be over here. They're both going to go to the same B0, okay? So even though they both equal B0, we don't know that these two are the same number. However, both A0 and A1 are elements of A0 union A1. That means that f of A0 is an element of the image of A0 union A1, and f of A1 is an element. Okay? So whether we have A0 or A1, whichever one of these is giving us B0, in either case, B0 is an element of the image of the union. And that's what we needed to show. We started with an arbitrary element of the union of the images, and we showed that in either case, that element is an element of the image of the union. Okay, so we proved inclusion in both ways, so this one is true too. So next up is that the image of the intersection of A0 and A1 is a subset of the intersection of the two images. But this is this is where the image operation breaks down. This is not necessarily true going the other way, unless F is injective. Okay, so first we'll prove this, then we'll prove going the other way, but we'll have to use injectivity in order to do it, okay? So again, the intersection of A0 and A1 may be empty, in which case there's nothing to prove. But if not, let B0 be an arbitrary element of the image of the intersection of A0 and A1. That means that there exists an A0 which is inside the intersection such that f of A0 equals B0. That means that A0 is an element of A0 and an element of A1. Now, A0 inside the subset A0 means that f of A0 is inside the image of the subset A0. And A0 inside A1 means that f of A0 is an element of the image of A1. So since this, and remember that this equals B0, so that means that if it's in both of them, it's in the intersection. Therefore, B0 is an element of the intersection of the image of A0 and the image of A1. Okay, that part's easy, that part's good. Now we have to prove it the other direction. So when we're trying to do this, we should run into trouble at some point, and it's going to require injectivity in order to complete the proof going this way. So we need to show that the intersection of the two images is a subset of the image of the intersections. Now remember again, this intersection might be empty, in which case there's nothing to prove. Otherwise, let B0 be an element of the right side. That implies that it's an element of both. So B0 inside the image of A0 implies that there exists an A0 inside A0 such that B0 equals f of A0. And B0 inside the image of A1 means that there exists an A1 inside A1 such that B0 equals f of A1. Okay? We're getting good at this, right? Okay, so this is the spot where injectivity is needed. We can't say that A0 and A1 are in the intersection of A0 and A1 because, as I just said a minute ago, A0 and A1 could be different elements in completely different subsets and still evaluate to the same B0, okay? So that's not good enough. But injectivity fits here perfectly because injective means that if f of A0 equals f of A1, that implies that A0 equals A1. Basically, injective just means that this can't happen. It means that the function doesn't double back on itself, so it's not possible for two separate elements in two separate subsets to evaluate to the same value. So this is exactly what we have here, right? F A0 equals B0, and it also equals A1. Since we know that F is injective, that means that A0 equals A1. So since these are the same value, therefore, both are in the intersection of A0 and A1. And therefore, B0 equals FA0 equals FA1 is an element of the image of the intersection of A0 and A1. So injectivity guarantees that the image of a subset preserves intersections as well. We won't bother to do set difference, but it's the same thing. you're going to need injectivity in order to prove the second inclusion. Okay, that's it. We've done a lot of work, and I think it's been really useful because we're experts now at manipulating these images and pre-images and elements inside one and what that implies and how to go back and forth and how surjectivity and injectivity affects these operations. So good. Okay, we're done now with our look at these operations for functions. So now with this in hand, next week we'll go back to finish our proof of the cardinality of finite sets. Thank you. Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe. And please join me on Patreon. The link to that is below in the description. Thank you.